Good morning, my YouTube viewers. It's Crystal here. I'm just here this morning because I want to make you another video, a code review. And on this code review, we're going to review the naive Bayes algorithm. And so basically, we're going to compare a made-from-scratch naive Bayes algorithm with sklearn's off-the-shelf algorithm, so you can see which one performs better. So we've written this program on Google Colab, and I've just written this program as part of a long program for my Eureka 10-hour course I'm taking. And the first thing we're going to do is we're going to import our libraries. So we're going to import Numpy as MP, which is a numerical computation library. We're going to import Pandas as PD as a data processing library. We're going to import matplotlib.plt.pyplot as PLT as a graphics library, and we're going to import Seaborn as SNS. It's also a graphics library that has statistics in it that's written on the back of matplotlib. And after we have imported our libraries, what we're going to do is we're going to use Pandas to read the Pima Indians diabetes data set into the program, which we've done, and we call that data. And you can see that when we read it in, it talks about, you've got a column on pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, degree function, age, and outcome. And then so the outcome is going to be either a 1 or a 0. So I'm assuming 1 is yes, they have diabetes, and 0 is no, they don't. So we do a disk plot on the outcome, and you see more people don't have diabetes than do. And then we do data info, and so you see that all of the columns are either integers or floats, which is good because that means that we don't have to encode any columns to turn them into integers. Prepare a heat map of this data set so you can see that the columns or the features don't have an incredibly high correlation to each other. And then so what we do is we insert some code to try to remove the columns that have a high correlation. But since none of the columns had a high correlation to each other, we were not successful in removing any code. And now what we're going to do is we're going to take the data set and we're going to create a train and test set out of it. And we're going to use the Pandas sample function to do that. And then what the sample function will do is it will randomize the data set, which is what we want. We want this data set to be randomized. So train equals data.sample brackets frac equals 0.9, so that's 90%, comma random state equals 42. So that's your train set, the train set. So what they do is they randomize it, and then they randomize it, and then they only use 90% of the test set. And so test equals data.drop train index. So what you're going to do in the test set is you're going to drop all of the rows that are to do with the train. And so here's your test set. It's 77 rows by 9 columns, and you can see that it's been randomized, which is what you want. You always want to randomize your data set in the hope that you'll get a better accuracy reading. So now after we have created our train and our test set, what we want to do is we want to create our X train and Y train, X test and Y test. So Y train is the last row of the train set, and X train is all of the rows except for the last row in the train set. Y test is the last row of the test set, and X test is all of the rows except for the last row in the test set. And then we check our shape to make sure that the shape is okay. Okay, now what we do is we insert the code to get statistics from the data set. So means equals train.group by outcome dot mean, and that's the estimate mean of each class feature. Var equals train.group by outcome dot var, that's estimate the variance of each class feature. Prior equals train.group by outcome dot count over len train dot ilog brackets colon comma 1. And that's estimate prior probabilities. And classes equals np dot unique train outcome to list. So that gives you, stores all the possible classes. But in this instance, it's only going to be a 0 or a 1. So now this is the made from scratch naive Bayes. So you've got your normal function, and what your normal function does is it defines your standard deviation, and it defines a PDF. I'm not sure exactly what PDF stands for. Let's see. It's no. We just carry on with it. PDF is something that I don't remember exactly what it stands for, but that's something. And then we're going to do our prediction function. And so you've got predictions equals square brackets for I in x dot index, because predictions accepts x in there. Class likelihood is a blank array. Instance equals x dot loci. For CLS in classes, as you look through each class. And then feature likelihoods is a blank array. Feature likelihoods dot append, say np.log brackets prior CLS. So you append log prior of class CLS. For call in xtrain dot columns, data equals instance call. Mean equals means brackets call dot loc CLS. You find the mean of the column call that are in the class CLS. Variance equals var call dot loc CLS. Find the variance of column call that are in class CLS. Likelihood equals normal data comma mean comma variance. If likelihood is not equal to 0, likelihood equals np.log likelihood. Find the log likelihood evaluated at x. Else likelihood equals 1 over length of train. Likelihood, feature likelihoods dot append likelihood. Total likelihood equals sum feature likelihoods. Let you calculate your posterior. Class likelihood dot append total likelihood. And then I think that finishes the for loop. And then so it says max index equals class likelihood dot index brackets max brackets class likelihood. So there you find the largest posterior position. Prediction equals classes max index predictions dot append prediction, and then it returns your predictions. So that wasn't too bad of a function. So now what we're going to do is we're going to predict. Prediction equals predict x train, and prediction equals predict x test. And for some reason that didn't run all the way. So we'll run it again. For some reason it didn't run all the way. Maybe I went through and did some work on it. Okay, so we did our predict train and our predict test, and now we have a function to define the accuracy, and the accuracy will take in a y value and a prediction. Y equals list y, prediction equals list prediction, score equals 0. For I, j in zip y, prediction, if I equals j, score equals score plus 1, return score over length of y. And so we talked about that in a prior video where for loops are slow, and there are actually functions that you can use that don't involve a for loop that are quicker. But this is code that I got from a website. It's not my own code, and I didn't want to mess around with it too much in case it didn't work. So we print accuracy of training set, and you have a 75.5% accuracy, and then we print accuracy of testing set, and we have a 80.5% accuracy. And so now what we're going to do is we're going to compare this with sklearn naive So from sklearn.naive import Gaussian NV, model equals Gaussian NV, brackets dot fit x train y train, print model score x train y train. So we had a 75.6%, which is higher than the accuracy we got from the made from scratch version. And then now we're going to predict on the test set, model.predict x test, print model.score x test y test. We had 80.5%, which is exactly the same as what we had with the made from scratch version. So the outcome of this is that although the accuracy of the made from scratch version on the training set was just slightly lower than that of the made from scratch, the off-the-shelf version, the accuracy of the test set was exactly the same. So that means that the made from scratch version performs the same as sklearn. So it's up to you whether you want to use a made from scratch version or an sklearn, but it's always good to know how these algorithms work, which is why I'm going through all of the algorithms. So thank you very much for watching my video. Thank you very much for supporting my channel. If you like this video, please like, subscribe, and share. And I look forward to making more videos for you in the future.